Hello, this is Dr. Gardner. In this tutorial we will be naming molecular compounds, and so we'll look at some general rules for naming molecular compounds. You will see we'll use a unique set of Greek prefixes when naming most types of molecular compounds in this tutorial. Now the first thing I look for when I have a molecular compound is that I should have only nonmetals or perhaps metalloids in some cases in my formula. We will notice that sometimes common names used in our society can appear for certain molecular compounds, but we're going to learn the rules for very specific nomenclature, naming rules for naming these molecular compounds using Greek prefixes. Let's look at a couple of examples of compounds that might have common names used for them. So if you see H2O, the common name that probably everyone in our society is familiar with is water for H2O. We have seen NH3 listed as ammonia. That's a very common name in our culture. Certain types of hydrocarbons will have common names. For example, natural gas, one of the main components is CH4 methane. We can also see an allotrope of carbon, which has 60 carbons in a shape like a soccer ball. This is sometimes called a fullerene, or in slightly looser naming, you'll hear them called buckyballs, named after Buckminster Fullerene, the architect who produced geodesic dome structures and architecture. But these are common names we might run into, but we want to follow some systematic naming rules, learn our systematic naming for molecular compounds. So the first thing we want to do with systematic naming is learn a few Greek prefixes to indicate the numbers of each type of atom that could be in our formula. Okay. Now, what we will start with the name is we often will have the leftmost element on the periodic table listed first. Really, what we usually list first is the more positive of the two elements with respect to their electronegativity that we will be seeing later on in the course. So, leftmost element or more electropositive element first. So, the last element that is named with respect to a molecular compound will have an IDE ending added. Now be careful, this does not indicate a monoatomic anion. It's just a standard technique they've used with molecular compounds. I can tell they're still molecular compounds because I will have no ions present in the formula. I will have just my nonmetals usually in the formula, even though the ending has an IDE. I also look for my Greek prefixes. That'll remind me that I wouldn't have a Greek prefix on a monoatomic ion. So if I see a Greek prefixes in the end of the name with an IDE, that indicates a molecular compound, not an ionic compound. So be quite careful, even though we see that IDE ending. Now the Greek prefixes indicating the number of atoms I have in the compound are the following. If I have a single atom, I use mono as a prefix. However, realize the first element in the molecular compound name, if there's only one atom of that type, we often will exclude the mono. The second element, however, we usually would include the mono on that compound. For example, carbon monoxide has one carbon. We didn't use the mono prefix, but the single oxygen in carbon monoxide did use the mono. So we leave it off the first element sometimes. Now, if I have two or more of that atom of that element, we do want to use our Greek prefixes. So if we have two of an atom, we use di. If we have three, we use tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. A lot of times students will need to focus on hepta. They have a little bit harder time learning that Greek prefix. Perhaps they've heard it used a little less frequently in our culture. Then if I have 8 of an atom, I would use octa. 9 would be nona. Again, that one can be a little tricky for students, so make sure you learn that nona is 9. If we have 10, that's deca. And that is all of the Greek prefixes I would like you to learn for this course. Okay? I want to remind you, if the first element only has one atom, we usually will omit the first mono in the compound formula. So we'll see some examples of that. Okay, so let's practice naming a few compounds. The first compound we're going to start naming, we're going to look at its formula. It's HF. Now, if I have this compound dissolved in water, we would name it as an acid and use the acid naming rules for a binary acid and name it hydrofluoric acid. If, however, I have HF not dissolved in water, I would use the molecular naming rules. So I would call this hydrogen fluoride or hydrogen monofluoride. Okay, both names are acceptable. Here we sometimes break the rule of using the mono at the beginning of the second element, but if I wanted to follow strict naming rules, I would call this hydrogen monofluoride. But a lot of times, unfortunately, in our culture, we have broken that nomenclature rule. The rest of these will follow a little more closely. So if I see silicon as the first element and oxygen as the second element, I would start with naming the first element. There's only one of it. As you recall, we exclude the mono. We omit the mono as a prefix when I have only one of the first element. So I would name silicon, and then the second element, you'll notice there's a subscript 2 after it. There's 2 oxygen atoms in the molecular formula. So we would use a di there. So I would call this silicon dioxide. Now next we see NO. There's a single nitrogen atom, a single oxygen atom in this molecular compound. It's all non-metal, so it's molecular. We would name the first element but exclude the prefix since there's only one nitrogen. The second element, oxygen, I want to add my prefix. This would also help prevent me from confusing it with the oxide ion by using the Greek prefix mono. So I name this nitrogen monoxide. I know that is not an oxide ion because I would not use a Greek prefix when I had an anion. So this is molecular. I also know it's molecular because I only have non-metals in the formula. I also would not confuse this with an oxoanion because there is no charge. So don't confuse this with my hyponitrite ion. It is not charged, so I name this as a molecular compound. Nitrogen monoxide is the correct name. Now if I have a nitrogen and 2 oxygens here, I would name this nitrogen for the first element. I omit the mono on the first element when there's only one atom. In the second element there are 2 oxygens, so I use the di. So I have nitrogen dioxide. If I have NO3, again I would name it nitrogen. Now I have 3 oxygens, so I use the Greek prefix tri. So nitrogen trioxide. Now if we have 2 nitrogens and an oxygen, well, the first element, since there's more than one, we start adding the Greek prefixes. So I would use dinitrogen for the first part of the name, for naming the first element, indicating how many atoms are present in the molecular compound. And the second element, since there's only one, we do keep the mono. So it's dinitrogen monoxide. You'll notice that we tend to drop a vowel off when we add the Greek prefix if there's a vowel present at the beginning of the element name. So I've excluded an O from the mono as I combine it with the oxide name. If I have 2 nitrogens and 5 oxygens, I'm going to use my Greek prefixes for both the first element and the second element. So I'm going to show dinitrogen as the first part of the name. Then I name the second element present in the molecular compound with the Greek prefix. There's 5, so the penta, since we would be putting 2 vowels next to one another, goes to a pentoxide. We exclude one of our vowels. Okay, now if I want to take a molecular name and go back to the formula, it's usually quite simple. So let's say we're seeing sulfur dioxide. Since the sulfur doesn't have a prefix shown, we assume there's only one. Since we have a dioxide, the di indicates 2 oxygens in the formula. So we have sulfur and 2 oxygens, so I show SO2. If I read the name sulfur trioxide, we would have just 1 sulfur since a prefix wasn't shown in front of sulfur, and the tri indicates 3 oxygens in the formula, so I would have SO3. I'm showing a subscript after the second element here to indicate that there are 3 of those atoms in the molecular compound. Now if I look at phosphorus trichloride as my next name, since the phosphorus doesn't have a prefix, I only have 1 phosphorus atom. The tri tells me there's 3 of the second element, chlorine, so I have PCl3. So those Greek prefixes will be quite helpful in molecular compounds. They tell me exactly how many atoms are in the formula. If I don't see a Greek prefix, we assume there's only 1 of that type of atom in the formula. So if I read tetraphosphorus hexoxide, we would know that tetra in front of phosphorus represents how many atoms? Be 4, right? 4 for tetra. The hexoxide indicates 6 of the oxygen atoms. So I have 4 phosphorus and 6 oxygens. So I would go ahead and show the formula as P4O6 with my subscripts after the element symbol indicating how many of those atoms are in the formula shown. Okay, so the next thing I will look at are chemical formulas where we have a difference between the molecular formula and the empirical formula. A molecular formula shows the exact number of atoms of each element in the smallest unit of that compound substance. Now, if I have a molecular compound, that's going to indicate the exact number of atoms in that molecule, which is going to be a unique unit. That's the smallest unit of that substance I would have. An empirical formula would be the simplest whole number ratio of the atoms present. We will see later on as we start analyzing unknown compounds in the course that my empirical formula is usually what I can find experimentally first. So empirical formulas we'll find first. Sometimes they'll differ from the molecular formula. There are some compounds where the molecular formula may be identical to the empirical formula. Let's look at an example of that. If I have H2O, water, the simplest whole number ratio of those atoms would be 2 hydrogens and 1 oxygen. That happens to be the same as the empirical formula since it's the simplest whole number ratio. But not all compounds will be the same. If I have a simple sugar, if I'm looking at a monosaccharide where I have a single ring structure for the sugar, here's, let's say, glucose, has 6 carbons, 12 hydrogens, and 6 oxygens in the molecular structure, that's not the simplest whole number ratio. So the molecular formula here for that molecular compound will be different than the empirical formula. If I simplify that ratio to the lowest set of whole numbers, I'm going to get a 1 to 2 to 1 ratio. So my empirical formula would be C1H2O1, and we exclude the ones if we don't show a subscript after the atom symbol. We indicate that we only have one of that atom present. Now your ionic compounds will usually show empirical formulas because we have the simplest whole number ratio of the ions present in order to balance charge. Because I do not have discrete molecules, I have really just an ionic lattice maximizing attractions between dissimilar charges and minimizing repulsions between like charges. So calcium chloride is an empirical formula. Sodium chloride is an empirical formula. Almost always ionic compounds will be shown as their empirical formulas. The only cases where that would not be true is if we had a polyatomic ion, let's say like mercury 1, where there was 2 mercury atoms in the polyatomic ion formula, and I would lose the identity of the polyatomic ion if I simplified the formula to an empirical form. So that only occurs rarely. So almost all ionic compounds you run into will have empirical formulas. Whereas some molecular compounds like water, dihydrogen monoxide, would have the same molecular as empirical formula, but many would not, like the glucose simplifying to CH2O. So recognize the difference there. We'll be revisiting those when we start determining unknown formulas for compounds later on in a few chapters. Now I want to show you how in our society many types of common names will differ from the systematic naming rules we're learning. So let's look at a few common names for molecular compounds and see how our systematic naming rules would name these compounds, so we can see where I might run into some other names for these chemical species. So if I start with water, H2O, if I use my systematic naming rule for a molecular compound here, I know it's molecular because there's only nonmetals. I have no ions present, so I have 2 hydrogens and an oxygen, so I would use my Greek prefixes if I use systematic naming. So water could also be called dihydrogen monoxide with my Greek prefixes. A common name you might hear in a society is lye. Lye is sodium hydroxide. So I would name the systematic naming. Here I name sodium first, then hydroxide. It's really not a molecular compound. This is a base. So perhaps I should have put it with the ionic compounds here in a minute. I did not swap it. If you hear of dry ice, not only does this tell me a common name for a compound, it also tells me the state of matter we're discussing. So we're looking at CO2 in the solid state for dry ice. The systematic name for CO2 is carbon dioxide. The dry ice specifically, though, is carbon dioxide as a frozen substance in the solid state. Laughing gas. There's 2 nitrogens and an oxygen in the formula for laughing gas, N2O. If I use my systematic naming rules, I could use my Greek prefixes to call this dinitrogen monoxide. However, we'll see sometimes this called nitrous oxide, which does break our systematic naming rules. I would like you to learn the systematic naming rules, so I'm kind of expecting you to use the dinitrogen monoxide now, even though you'll also see the name nitrous oxide out there in our society. Let's look at a few more ionic compounds and some common names for those, as well as systematic names. Now, if you hear somebody say table salt, they probably are referring to an ionic compound, NaCl. The systematic naming rules we've learned for ionic compounds is I should name the cation first, followed by the anion. So I would use just the metal name for the sodium cation. So I just use sodium, and then the anion is a simple monatomic ion, so I have chloride with an IDE ending. Now I know not to confuse this with the ides in my molecular compound because there is no Greek prefix used. That helps us differentiate between the two. Now if I have marble or limestone, I would have one of the major components present in ionic compound that has CaCO3 as the formula. If I use systematic naming, I would notice this is ionic in nature. I see a cation followed by an anion. I name the cation first. This metal would form the calcium cation. There's only one possible charge state, so I do not use any Roman numerals. And then I have carbonate for my anion. This is one of the common anions I asked you to learn first with the ATE ending. There's a -2 charge on the carbonate ion, so that would balance the charge of +2 on the calcium ion, which I know from it being an alkaline earth metal. It's in the second group on the periodic table, the second column. So this is calcium carbonate. Quicklime is a common name for CaO. Now if I use my systematic naming rules for this, I name the cation first, which would be calcium. Then I name the anion, which would be oxide. The calcium has a +2 charge as the cation here. The oxide has a -2 charge. So let's just name it as calcium oxide. Slaked lime would be calcium hydroxide, where I name the metal cation first, followed by hydroxide. This is also the name of a base, so you realize we're using ionic naming rules for naming many of our bases. I had to have 2 hydroxides in the formula, so I showed brackets around the polyatomic ion to indicate multiple polyatomic ions, and they have a -1 charge each, so I needed 2 hydroxides to balance the +2 charge on the calcium. Baking soda in your kitchen would actually have the sodium cation followed by the hydrogen carbonate ion. So I have to be careful. I'm using my anions, my oxo anions, which have hydrogens as part of their formula. So I have to be careful to recognize the 2 ions here. I know not to name this as a molecular compound because there's a metal present at the beginning of the formula. So I am following ionic naming rules. So I name the metal ion first, sodium, followed by the anion name, which would either be hydrogen carbonate, which would be completely acceptable, or it's also known as bicarbonate. So sodium bicarbonate or sodium hydrogen carbonate, both the correct name for this with our systematic naming rules. Now you may have milk and magnesia at home when you're having issues with respect to your stomach. Milk and magnesia has the formula Mg and then OH in brackets with a subscript 2. Now if this is an ionic compound, the metal forms a +2 charge cation. I know this because it's in the group 2, the alkaline earth metals, and hydroxide has a -1 charge, so I needed 2 hydroxides to balance here. So I just named the cation first, followed by the anion name, so magnesium hydroxide. You'll notice we're also naming this as a base. This is following the ionic naming rules. So now that we've practiced a few, go ahead and continue to practice naming molecular compounds. Realize sometimes in our culture we do use common names, but I will, in this course, try to use my systematic naming rules in most cases. Thank you.